Hi everyone, it's Judy Warner. Welcome back to the podcast. Today I'm going to share with you a delightful man who is Alun Morgan, who's the technology ambassador for Ventec, which is a world-class PCB laminate manufacturer. He'll teach you about his lifetime of understanding material science and how that will impact you and the materials you choose for your designs. So lean in and enjoy. I'll see you on the other side. Welcome to Altium's OnTrack podcast, where we talk to leaders about PCB design, tackling subjects ranging from schematic capture all the way to the manufacturing floor. I'm your host, Judy Warner. Please listen in every week and subscribe on iTunes, Stitcher, and all your favorite podcast apps. And be sure to check out the show notes at altium.com/podcast, where you can find great resources and multiple ways to connect with us on social media. Well, Alun, thank you so much for joining us today on the podcast. We're looking forward to learning from your vast wisdom of material science. So thanks so much for joining us.
It's a pleasure.
So why don't you start out by telling us about your background? I know you have a rich background in material science and in the industry. And then tell us about Ventec.
Yes, I'm a material scientist. I graduated many years ago in metallurgy with materials technology. In fact, in my final year of university, I was busy making epoxy resin reinforced glass fiber materials, so quite similar to what I do today, actually. I moved on from there. I started work in research, first of all, with the Institute of Physics in the UK. I then moved into PCBs. I spent 2 years manufacturing PCBs and then really got the bug. And PCBs are a fascinating topic for a material scientist because so many materials are involved in the process of producing a PCB. So I moved from there to work for a major laminate manufacturer for the rest of my career. Various roles, corporate VP of engineering and technology. I've run various facilities, had a lot of different roles in that sphere. So my entire career really has been in electronics manufacturing or PCB materials manufacturing.
Well, I think it's really fascinating that you have hands-on, right? Not just working for a laminates manufacturer, but actually getting your hands dirty in the process.
Yes, I mean, I've also set up some plants, and that's quite fun because when you have people don't probably realize laminate manufacturing is big scale, and we're talking about very large machines, very big investments. And to set these things up takes a bit of doing, So, I've got my hands very dirty, covered in resin, covered in all kinds of things. And it's important, though, to understand the process. And I think, people who've had a career like mine do understand the big scale of stuff. So we make sheets of laminate that are, sometimes 8 foot by 4 foot in size. We make thousands at least hundreds at a time, thousands in batches. And we have to control the process very, very critically. Very carefully because
Alun, about the scale, aren't some of those, I don't know the proper name, maybe the laminators, the coaters, whatever, like room size, right? That are making these sheets of material.
No, they're massive. They're multi-story building size. I mean, they are huge, very large bits of equipment where glass fabric is coated with resins, and I'll come in a bit later to explain about the process a bit more. Okay. But yeah, huge bits of equipment, and the presses. Again, presses can be 20 or more than 20 openings. They are the size of a building. Some of these presses apply 4 tons of pressure. So really very, very large bits of equipment. And of course, when we see the multi-layer lamination process, this of course is much smaller scale, but the same principles apply. So what we learn from manufacturing the materials to very close tolerances, we can also apply in developing materials so that manufacturers can manufacture multi-layer PCBs with the same kind of quality and the same kind of process control to reduce the variability in the final product. So it's a very good training to make PCB materials. It's big scale, but everything that we do can be related exactly to making PCBs as well.
That's interesting. I've never seen one of those. I've only heard about them, but I've heard that these machines are massive, and it's sort of hard for me to imagine how large they are. So tell us a bit about Ventec. So your role at Ventec right now is a unique one. sort of like my own a little bit, and that is that you're a technology ambassador. So tell us about Ventec and tell us what a technology ambassador does.
Well, Ventec is a global PCB materials manufacturer specializing in advanced copper clad reinforced materials and metal back materials and substrates. So Ventec has volume manufacturing in China and in Taiwan, and worldwide distribution network through the US and through Europe, and of course through the rest of Asia. So Ventec is a high-end manufacturer, let's say, of these kind of products. The ambassadorial role is interesting. I mean, I love technology. I've always loved technology my entire life. So being an ambassador for a technological company is like a dream for me. So I can actually interact with customers around the world and also with Ventec themselves. So we work together. I try to bring to the company latest developments from the market and requirements from the market, and that can be then used to developing new products. And of course, on the other hand, I'm also promoting the various materials that Ventec has. You know, there are a number of specialized areas. I mentioned metal back materials. That's one area. There are very high reliability materials. The polyamide range is also very important, and the high-end epoxy reinforced materials, which are the mainstay of business. And I'll come on to describe a bit more of what they actually are as we move further on. But yes, it's a great role for me. I really enjoy doing this, and I shall be off next week to China to a large trade show where I shall be spending time with Ventec, of course, and with the EIPC, which is the European Institute for the Printed Circuit Community, which is another role that I have. So we're meeting with old friends and looking at customers and looking at new requirements for the market.
Sounds like a career of passion and great interest. And I share a little bit. I don't know as much as you know, Alan. However, I always tell people here at Altium that I feel like my role is just to be a bridge, right, between Altium and the industry and Altium. I just feel like I'm the bridge. So it sounds like you're playing that same sort of role, which is a really important one, because the two can get detached sometimes. And
yes, and manufacturers go through different phases. Ventec is in a very strong growth phase, which is quite exciting right now. And in the last or recent years, there's been a lot of changes in the technology that we have to deploy. So that means it's been pretty challenging and exciting, in fact, because for many years there were very few materials available. Now in the last 20 years or so, there's been a complete opening up of this market. So now there's no end of materials, no end of solutions, no end of requirements, and actually threading your way through this maze for designers is becoming quite difficult. And I see my role, for example, is to try and explain and cut through some of this complexity so people can understand what really matters and select things that really matter to them without all this confusion and let's say proliferation of products all around them. I would hate to be a designer from the outside now looking in and trying to choose where I'd like to go, because you have so many choices. In fact, probably too many choices.
It's so true. And that is an excellent segue into our conversation. So what I wanted to talk to you about today is that very thing. I think designers today and EEs that are designing boards are swimming in this vast amount of availability of different materials and how do they pick and how relevant are data sheets. So I wanted to sort of give our listeners today, from the master himself, materials 101. So let's start with a little bit of history, kind of like where we started and then get to where we are today. And then, maybe a few steps on how to get through this maze. So, the most standard material today, is still FR4. So why don't you talk a little bit about the history of FR4? What does FR mean in FR4? And just give us a little thumbnail of the history.
Yeah, the FR4 we use today has its roots really around 60 years ago. So we go back quite a long time. Of course, there's an FR4 today. As you might imagine, there was an FR1, an FR2, and FR3 as well, and FR5 for that matter. These all came out of a specification from the early 1960s, which is the NEMA specification called LI, which defined these things. So FR just means flame retardant. That's all it means. There are other grades. There are grades called G1, G2, G3, and G4. These, or G10 was a very common material as well. The G meant non-flame retardant. So that was the distinction we could find straight away from the beginning. So FR4 basically means it's the fourth generation of materials in the NEMA classification system. And what that means is it defines the resin kind and the reinforcement kind. And just to explain what that means, all PCB substrates have two real parts. One is the conductor, which is copper generally, and I think we all understand how that works. The rest of it, though, is the substrate. It's the insulating material. Now, for most people, that's a kind of green thing that the circuitry sits on.
Right.
But actually, the green thing is a bit more than just one thing. It's a composite material. It contains a resin and a reinforcement. The FR4 means an epoxy resin, like the kind of stuff you use to patch up stuff in your home, epoxy adhesives. And the reinforcement is typically glass fibers, woven glass fibers. Not quite the stuff you patch up your kayak or your vehicle or your automobile with, but very similar in style. So it's something that gives a mechanical strength to the material. So the substrate itself is a composite of these two materials, resin and reinforcement, and the conductor is copper. You can use other reinforcements, other resins. So if I would just roll back to FR1, I mentioned earlier, FR1 was pretty much a low-graded material designed for low-end consumer applications, so the TV sets, radio sets, that kind of thing. And that was made of a reinforcement of paper sheets, literally. So just imagine craft paper sheets impregnated with a very low-cost resin, which was a phenolic resin, resin system. So that was the cheapest material you could buy. You could punch it very easily, so process costs were low. But of course, there were some issues. Stability was pretty difficult with the paper rather than glass, so it would move around while you're trying to process it. So trying to get tight features and precision on features was very difficult. And the resin, the basic resin was a very basic resin. It was very moisture absorbent. It wasn't particularly good at insulating either. So down and dirty, I guess, would be the term that will be used. And still today, that material is available, and people are still using it for those kind of applications. But as you said, Judy, things have really moved on to FR4 being the staple.
Right.
And that's interesting that for more or less 60 years we've had the same basic structure of that material.
It's true.
It just shows you how good it was actually, and how smart the people were who first of all came up with this.
Yeah.
The glass fiber for sure has changed over the years, and we'll explain a bit more later. And the resin for sure has changed over the years, but they are still basically the same construction that we used 60 years ago.
And just for clarification, I think it's obvious, but again, Materials 101. So the glass weave that's inside the resin structure provides stability in the X and Y coordinates, right? So it won't move during processing of the board fabrication, right? So it doesn't stretch, and so it lends to good sound registration and things like that, correct?
Yes, there's more to it though. It wasn't really designed for that originally. It was designed originally because if you look back to circuit boards some 50, 60 years ago, these contained pretty big components, big transformers, large elements, and actually you needed it for strength, because the FR1 materials would crack if you put big things on them. The glass fiber is very resilient. It's very, very strong in tension, so you could stick big transformers on there. If you look on the back of your TV set from the 1960s and 70s, you'll see it had these huge components there. So actually it was needed as a mechanical component as well.
I see.
And that's interesting. To some degree we still do that, although components are much smaller now. But you will often find a circuit board is actually a structural component of a device. So the board is screwed and it forms part of the structure. So it's still required for that as well. So stability for, let's say, consistency and process, it doesn't move around. And secondly, to give this strength so it doesn't crack and fail in service life. Okay.
So that's sort of the basis of where we started, like you said, 60 years ago. And it is really impressive. I mean, I started this industry in the 80s, and FR4 was designed long before that, and it's still around and still sort of the basis of most boards these days. Now, let's dig in a little bit more to those resin types. I know that's something you know a lot about, and the composites a little bit more. And why? Why each one? How can we teach the engineers that are listening about Why we even use this stuff?
Well, the main reason why we use epoxy resin is because it's very strong. It's a very good electrical insulator. It's strong and it's available. So that's why epoxy became the sort of de facto standard for these materials. It's also possible to bond it to glass fibers very, very well. Also, the glass fibers that we use have special treatments on the surface that actually will form a chemical bond directly through what's called a silane treatment to the epoxy resin. So we're not talking of mechanical connections here, we're talking of chemical connections. So we can actually chemically link the resin to the glass fibers so they don't fall apart, and that's a very important thing. So epoxy came around for those reasons. Epoxy resins are used in many things. I'm sure we know in construction. They're used in paints, they're used in tin can coatings. Inside of cans are coated with epoxy resin. It's very resilient. It doesn't have a particularly high water absorption. It's very strong and it's available. That's the main reason why we use epoxy. The other resins that are around, I mean, if we think back, to a few years ago when all this started, I mentioned phenolic resins. They were the sort of low grade, cheaper materials. Epoxy resins took the kind of professional part of the market, but there were other kinds as well. And we used to classify our materials based on the chemistry. We would have other materials like a material called polyimide material, for example, which going back 20 or 30 years was the only material really available that would survive very high temperatures of soldering. So it's used typically in military and aerospace applications where you want to be able to repair these articles in the field with soldiers, using pretty uncontrolled equipment, so pretty robust. They call it soldier-proof material. So that was a standard. And then, of course, there are other things came along that people were concerned about signal integrity at some stage. So a lot of these materials are quite lossy. When I say lossy, what I mean is when you input a signal through them, you lose part of that signal. The reason for that is that the structures of them are quite polar. So it's possible for the material to actually absorb energy from the signal. So materials that are not polar, like PTFE, for example, came along. PTFE is very unpolar because it has a backbone of hydrogen with fluorine atoms distributed along it. Fluorine is a very electronegative compound, atom. So this structure forms itself rigidly in place. It really can't move around. The atoms are locked in position. And if they're locked in position, they can't move. If they can't move, they can't expend energy or consume energy. So there's a whole range of materials that came along like that. So if we think back to the beginning, so we have phenolic resins, we have epoxy resins, we have polyimide resins, and we have PTFE resins. And these are kind of, if you like, the starting place where we came from. But of course, over time, people have said, well, actually, I quite like the epoxy. It's really good. It's very good to process. It works really well. But I wish it was a bit less lossy. So, of course, people started to work on it. I said, okay, let's see if we can do something about that. So they reformulated some of these materials to make them less lossy, for example. Or they said, I like PTFE. It's a great material. The loss is wonderful, but I can't really process it very well. So couldn't you make it a bit like the loss, but give me a better process? Couldn't you work on that? So yes, we can do that. So chemists started to work again. So over time, you found a kind of, let's say, a derivation of all these materials, and all of them have been tweaked substantially to change for the properties that are required for today's market. Mm-hmm. And that's why it's quite hard now to actually say, I want an FR4. What is an FR4? An FR4, even within UL now, we have FR 4.0 and FR 4.1. UL recognized a long time ago. UL, by the way, is one of the main safety and standards bodies in the US, primarily looking at electrical and fire safety. They said, look, we've got this thing called FR4, but it covers a whole range of materials now. So just saying FR4 isn't really enough anymore. So they classified these in terms of how the flame retardancy is performed. So that's a break as well. So different chemistry leading to, of course, different performance. And that we have to bear in mind these days. You can't just say, I want to build my structure on FR4, because you could get 1,000 different products delivered that are FR4, but they're all different. Yep. And that wouldn't really be what you need anymore. Yep. So it gets complicated, Judy, as we move on.
As we know, I know. That's why we need you on this podcast, Alan, to help sort all this out. You had said to me too, so there's FR4 and all those classifications of FR4, because every manufacturer can offer these different FR4s where the properties can be slightly different. And then remember the fun days when we decided to go lead-free.
Yeah.
So talk about that a little bit.
They were fun days, and that was a real major change. So the basic story, it goes back around 20 years, I suppose. I mean, we've had a very long lifetime for this particular discussion. The issue was that lead had to be removed from solders because of ROS regulations in Europe or in the EU. So lead was going to be banned from electronic assemblies. For right or for wrong, by the way, I have my opinion on that as well, but nonetheless it happened, so we had to deal with it. So we used to use tin lead, a eutectic alloy of tin lead, which was sold at around 235 degrees centigrade. That was a standard reflow temperature for assembly. I think the eutectic melting point is around 180 degrees or thereabouts for tin lead. So the lead had to come out. You take the lead out, and of course a eutectic mixture does give you a depressed melting point. So we took the lead out and we ended up with other materials, primarily a sack alloys. So we're talking of tin silver alloys with a bit of copper in there as well, which then moved this temperature from 235 or thereabouts up to around 260 for soldering. So that was a bit of a step up in soldering temperature. And the problem was many of the base materials, the FR4s that worked fine at 235, when you tried to run at 260, they fell apart because they just couldn't cope with it. And even more annoyingly, for many people, some of these, let's say, alternative materials that have been developed for loss, to improve loss, they were the worst of all. So they could survive 235 fine, but at 260, they just really blew up. So suddenly, all these great things that were happening, all the boards were working, then suddenly you couldn't solder them anymore, and that was a major change to the requirement. So of course the chemists started to work on this and stuck with the epoxy resins. Epoxy resins are typically it's a so-called thermosetting material. I'll just describe this briefly. What it means is when you make this, you heat it up to a certain temperature and for a certain time, and it cures. It becomes solid and forms a permanent, really strong 3D cross-link network. It's the same as using sulfur to vulcanize rubber for your automobile tires. The same process exactly. So you go through this process and you form this structure. The curing system that was used was an inorganic curing system in days gone by, very commonly used in paints and many other industries, and there was a sort of single-digit percentage of this curing agent added to the material. The problem was, although this worked very, very well, at higher temperatures it would break down. So actually, these high temperature cycles, it really wasn't appropriate anymore. You could get away with 1 or 2 or maybe 3 cycles, but you certainly couldn't get away with the 5 or the 10, which are required by by manufacturers now. Mm-hmm. So people said, well, how can we deal with this? So let's find another way of sorting this out. So they changed the curing system. So instead of using the inorganic system, which I'll call it dicey, just to give it a name, we moved from single-digit percentage of dicey to double-digit percentages of using another resin system to cure. We call this phenolic curing agent, a bit like the stuff I mentioned first of all, and the phenol molecule, the phenol molecule, which is a benzene ring with an OH group attached, is very common in organic chemistry. We use it in the epoxy resin as well, so it fits, and you can then cure the one polymer with another polymer. So this was a way to get around this. And if you look at the performance of this phenolic cured system, we took out this inorganic compound and made this thing entirely organic, and that gave us that extra few degrees that we needed to actually survive the soldering process. So that was really the first step. So you'll see people talking about phenolic cured FR4s or phenolic cured epoxy resins. That's what that means. That means we changed the curing system and it gave it a bit of extra space on the temperature. And we measure that by a decomposition temperature. So, there are data in data tables. If you look at every manufacturer of base materials, you will see a value that says TD, so decomposition temperature. For standard FR4s cured with the old way, you're talking around 300 and something, so 305 degrees centigrade, maybe 310 if you're lucky. When you move on to the phenolic cured systems, you'll find these go to 325, 330, even more.
Oh, okay.
So there's a step up, and you can see that step. And if you see a TD in the range of 330, something of that nature, that material will survive through lead-free soldering, multiple excursions. So that was the
I thought the only nightmare that lead-free created was on the soldering side. I had no idea there was this impact to materials. So that's really interesting.
It also causes other problems as well. We've talked about the survivability of the soldering process, which of course is critical. You've got to get through that before anything else happens. But then you've got lifetime to consider. So having gone through that process, how damaging was it to the base material and the board for the rest of its life? So did you take out 80% of its life or already 5% of its life? So how long will it now survive? So many people put in thermal cycling testing. So you take a material, you cool it down, you heat it up multiple times to simulate a lifetime of the material in use, and you see how it performs. Then you find interesting things as well. When you're using fairly high temperature ranges, you find the material expands quite significantly. So you mentioned before, the X and Y dimension is held in place by the glass fibers, which is great. So X and Y, we're pretty solid. And actually X and Y, the material expands and contracts, to put a number on it, let's say around 12 to 15 parts per million per degree centigrade. So it's pretty minor. Of course, in the Z-axis or the Z-axis, through the material, there is no reinforcement. It's only layers of glass and resin.
Right.
You have a much higher expansion rate. So typically, for the resin in its normal room temperature state, we're talking around 40 to 50 parts per million per degree C. But when you heat it up above what's called the TG, or the glass transition temperature, which is a kind of softening point of the material and ranges between around 130 and 250 degrees centigrade, above that it starts to expand much more rapidly. And we're talking about going from 50 ppm per degree C to 250 or 300 ppm per degree C, so massive expansions in that area. So that is a concern, and as we moved on with requirements becoming more demanding, so first of all a severe assembly process at high temperatures, and then taking an industry example, take automotive for example, where they require the product to survive in Arizona and also in Finland. So it's got to be cold, it's got to be hot, it's going to cycle between these two ranges. Add that in as well, and you end up with another performance issue. And the material that we modified to make it lead-free compatible, lead-free suitable for this higher temperature, became a bit more brittle, and also expands quite a lot in some of the dimensions. So this was another concern. So how was that dealt with? Well, it was dealt with another change in the chemistry, in the formulation. So we recognise the resin expands a lot. So why not put something else in there that doesn't expand as much? So then you'll hear about people talking about fillers or inorganic fillers and how they frame this.
Right.
So if you replace some of the resin with something that doesn't expand very much, then overall the material will expand less as well. So you can take a material, an FR4 epoxy that's been modified to use a phenolic curing system to survive lead-free assembly. We modify it further by adding what's called a filler, an inorganic filler, to reduce the Z-axis expansion.
What is that filler, Alan? Like what type of fillers? I know there's more than one, but what type of fillers? There's
lots. They can be silica materials, they can be talc-based materials. There are many of them. And to confuse the issue, I don't want to get too far down the rabbit hole, but some of these fillers can also have other properties imparted. So some can also be flame retardants. So there's a whole range of things you can put in there.
And will they affect performance, or can they affect performance as well?
They affect performance in lots of ways. They affect it in the expansion rate, first of all, and that's what we put them in there for.
Right.
So you put them in there to give you a lower expansion rate, which means that when you come to your thermal cycling, these materials survive better. And these materials are generally called phenolic cured filled FR4s.
Okay.
So you'll hear that term now and again, and that's something that's been modified to make it lead-free process compatible and can now withstand extreme thermal cycling. So that's a very common material you'll find. Of course, there are some issues.
What about the electrical performance? Can that be impacted?
Yes, it changes. It can be for the better or for worse, by the way.
Okay.
Some inorganic fillers actually have lower loss than the epoxy resin they're replacing. In fact, most of them do. So by using a filler, you can actually modify electrical properties as well. You can modify the dielectric constant of the material, which is the, let's say, the way it acts as a capacitor, or the capacitance of the material. You can also change the loss parameters, because many of these organic or inorganic fillers have a fairly rigid structure. They don't vibrate in the same way that, or they're not as polarizable, shall we say, as an epoxy epoxy resin system, so you can actually have improved properties. But on the downside, if you imagine, we're also going right back to the beginning. We have a conductor in the story as well. We have the copper, which we've got to stick onto the surface of this material somehow. And of course, the sticking bit is the adhesive, is the epoxy resin.
Yep.
If you take some resin out and replace it with an inert filler, it doesn't stick as well. So when you start
so your
doing
peel
that,
strength is compromised? Okay.
Can be compromised, so that leads to a whole discussion around how can that be improved. But whilst we're on that part, we're sort of moving down the path fairly quickly now. Of course, the conductor has a huge impact on loss as well. So when it comes to signal integrity, you don't really want the conductor to have a huge tooth on the back,
Exactly.
a massive profile. And to put numbers on that, copper foil typically that's used is between 18 microns and 35 microns in thickness. So typically half ounce is 17 microns, 1 ounce per square foot is 35 microns. Of that 35 microns, traditionally, even up to 10 microns of that could be tooth. Could be this rough backside of this material.
Yeah, so let's pause there for a second, again, because I want to think 101 here for some that may not know. If you look at copper, and Alan, you may explain this better than I, but there's a shiny side and there's a dull side of the copper foil that gets laminated, and that dull side intentionally has been treated to have a tooth for adhesion to the base material, correct?
Yeah.
Now, if you look at that under a microscope, it looks like the Himalayas. So if your signal's moving through that, you don't want your signal going over. It's impeding the signal. And so is that correct? Or
yeah.
Okay.
It is. And the reason for it is the copper foil is produced by an electroplating process. There's a very large drum, which is either titanium or stainless steel, and the copper is actually plated onto it. So one side is very smooth because it reflects the surface of the drum, and that's the side that you see. That's the side that you get to put your conductors on and to use in the PCB process. So you want that to be smooth and nice and shiny. The other side is very rough. It's deliberately done that way. It's plated at pretty high current density, so it's rough to begin with, and then more roughness is added because you want this to have a sort of a mechanical tooth. So when you stick this together with this resin that we're using, this actually grips onto these teeth and holds it in place so it doesn't fall off.
Which gives us great peel strength.
It does,
and it helps with reliability and all that. And again, when so many of these things, what chemical, what do you choose? What do you choose? And it's like, well, it depends on what performance you're trying to get, what thermal environment is going to be in. There's so many factors here. And so when it comes to signal integrity, though, a big fat tooth that helps with adhesion and peel strength is not ideal for low loss application. So
no, absolutely, and there are a number of issues around having this big tooth underneath. I mean, I'm sure designers understand that when you start increasing frequency, the electrons start to run in the outside of the conductor, the so-called skin
effect, right?
So the higher you go up, the more they run in the outside. Now at low frequencies, it doesn't matter at all. You can do what the hell you like. When you get though into gigahertz range, which we are for nearly everything these days,
right?
The electrons run on the outside. So imagine this: you've got a conductor there that's got two sides. One, as you pointed out, is very smooth. The other side is really, really rough, like the Himalayas. So there's two big issues. First of all, the signal path length is different. So the smooth one is a short path. The Himalayas is a much longer path. And secondly, it's a much higher resistance pathway as well, because it doesn't just contain copper, it contains other elements as well. So that rough side, the Himalayan side, does have components in there which are there as a barrier layer to avoid interactions between the copper and the resin chemistry. So you find this sort of so-called a passivation layer is the name of this, or there's many other ways it can be applied, but you do have this problem of this much longer pathway. So if I talk about a profile depth of 10 microns, I mean this is absurd. No designer could use that with a high frequency design. They'd laugh at you.
Right.
So many years ago, the powers that be decided to classify what they call a low profile foil instead. So rather than allowing 10 microns of roughness, they made it 5 instead. Now 5 sounds great, but it's twice as good, but it's still nowhere near good enough. 5 microns is still an absolute disaster for high speed signals.
And again, every time you lower those low profile, you think, oh, I've solved the problem, but no, actually you've created another problem, because then your peel strength can go down, correct?
Yeah, and imagine we're doing this at the same time that we're adding fillers to the base material, taking the resin away. So you've got a double hit, basically.
I don't know how we ever make a circuit board, Alan. It's just
No,
so complicated.
it's almost magic, isn't it? Really,
It really is. It really is.
So, of course, as it's gone on, though, and the amazing thing is, and the real I think the real point here is, how robust our solution has been, because actually we've managed to make it work still, and by tweaking and by changing things, it's been possible to continue this path. So if I told you now there are treatments that are called almost no profile, so ANP, and we're talking sub-micron in many cases now, so going from 10 microns to less than 1 micron,
Wow.
and we get pure strengths that are very similar. I have to say they're not quite the same, very similar. Some will tell you they're better. I'm not sure I believe it entirely, but if you if you think about that, and there's a number of ways of doing this. Instead of just relying on a mechanical bond, I mentioned before that we use a chemical bonding between the glass and the resin.
So is this your adhesive system then, Alan?
No,
or is it a treatment?
It's a treatment on the back of the copper foil.
Okay.
So the producers now can provide organic treatments on the back of the foil, which will actually chemically bond into the resin as well.
Oh, nice.
So they've taken the problem and they've moved it on as well. So having said that, though, people in the past used to expect 10 pounds per inch of peel strength or 1.4 newtons per millimeter. Now specifications run down as low as 6 newtons per millimeter. So probably less than half of what we used to. But on the other hand, we don't stick big transformers on there anymore. We don't stick these huge components there anymore. Mm-hmm. So we don't have this big problem of these things falling off. We don't have the issue, of course, either of the thermal unreliability of old systems. So in the past, you solder these boards. The resin wasn't that robust thermally, so when you soldered them, you could actually lift the pads or lift the traces off. Mm-hmm. Now that's much better because the resin itself is far more resilient to thermal cycling. So actually now when you solder them, there's far less tendency for the tracks to lift or the pads to fall off anyway. So there is some good news on that side. But overall, we can now run with sub-micron treatments on the foil. We can run with these greatly enhanced resin systems to actually give us a robust thermal resilience through the assembly process and through the life of the board as well, and we can address some of these loss problems as well.
Now, where are we with things like reverse treated, where we flip the copper and we put the shiny side down, which generally compromised peel strength, or reverse anneal or ED, or these different type of copper systems? Where are we with those? Because what you're saying sounds better in some cases than that, or is it just their trade-offs?
The reverse treated foil, which is a trademark process, actually was very innovative. It basically said, okay, listen, rather than apply this extra treatment on the rough side of the foil, we'll put it on the smooth side instead. So we get very, very small little peaks on the smooth side, and then we'll flip the whole thing over and we'll bond that to the substrate. And in North America, that was very widely used. Not so much in Asia or in Europe, I have to say, for other reasons, but very widely used, and was a good first stage fix and lasted for many, many years. Still today, that's a solution, and a good solution. But in the meantime, manufacturers have also thought about this and actually moved things on and improve the rough side as well. So all solutions are still available, and you'll still find reverse treat foils widely used, but there are alternatives now as well. You can get the same kind of performance without that particular process.
Wonderful. This is great news. I actually didn't know about that. Well, we're running shy on time, so can you just give our listeners maybe 2 or 3 things? First of all, for our listeners, don't be overwhelmed. We're going to share all kinds of resources in the show notes. Alan was one of our keynote speakers at Ultium Live in Munich. He did a beautiful talk. We have that on video, and also I can share the PDF there. Ventec, I'm sure, will share some resources so you can dig into this more, because obviously you're not going to learn everything you need to know or want to know in this short podcast. So never fear, we will share more information and help you get more up to speed. But Alan, as we get towards the end here, what are 2 or 3 things, or 1 or 2 things designers can think about? I would think if I'm a designer today, I'd be overwhelmed with the amount of information that's available. How do I read data sheets? Can I depend on data sheets? Like, can you just share a couple takeaways to help our poor listeners digest some of this and have some quick takeaways?
It is pretty difficult, I have to say, because you can look at the values on data sheets. You can believe that that's what you'll get in your final design. It's not always the case, because don't forget, when you're buying a material or specifying a particular material, this will have a variety of different constructions and different forms. So you might, for example, have a form that has a very high resin content and a very low resin content. They will change properties very significantly in the final product. So you can't really take the data on the data sheets.
You mean because they're all laminated together, say in the form of a multi-layer, or why do the properties change? Or because of the heat and chemistry they're...
It's because of thickness, simple as that. So if you specify a thick material, then typically it will have a lower resin content, and a thinner one has a higher resin content. That's the nature of impregnating glass fibers. That's how it works. It's often beneficial to have a high resin content, but lots of measurements are done at lower resin contents. I could give you an idea. For example, when people are measuring loss characteristics, the resin is quite lossy, so the less resin, the better. So quite often you'll see these measured at 40% or 50% resin content, and that's the data sheet value you'll see. And it's disclosed, you'll see that on the data sheet. When you come to your design, if you're making a 20-layer multi-layer board, you're almost certainly going to be using 70% resin content-ish. So you're quite a long way away from where the data was measured and the data was published.
So how do you get accurate data?
The way to get accurate data is talk to the manufacturers, talk to Ventec, talk to your suppliers. They will give you a table with every single construction, every single material, and those properties at different frequencies. So you can then see where you are in your design. You can then see exactly how that aligns with the materials offered. So you could be fairly sure that's where you come to with it. Many of the Altium included, by the way, many of the design softwares actually do have libraries from the manufacturers that contain that data as well. So you will be able to get access to that, but just be aware, you can't just take one data sheet value. One material is a whole suite of materials actually, of bonding layers, of core layers, copper foil types and styles. There's a whole range of different ways, even different glass fabrics. We haven't come on to that, but you can choose different glass fabrics that have different properties electrically. So there's a whole range of materials you can choose there. So use the design tools, but then also talk to the manufacturers, talk to the PCB house, ask them what their experience is, ask them what they use, and by all means, come and talk to people like Ventec, talk to us. We'll advise. And I guess the biggest question you should probably ask if you're talking to a supplier or a PCB shop is, what's the material that you use most? What do you find works best? I know it's perhaps the wrong way around to do it, but actually, you may see a manufacturer, advertising 100 different products. They may only really sell 4 or 5 because they may be the ones that really hit the sweet spot and work. So you have to try and get through to that point. Of course, on the other hand, be careful, because if you specify in that way, you may miss out on opportunities that innovative products may offer you. So quite often there may be a product that's ideally suited to your application. You'd never hear about it or come across it because you talk to the manufacturer who's never seen it before or never used it before. So do be aware, it's a very fast-moving area, especially in terms of signal integrity right now. 20 years ago it was in terms of thermal reliability. Now it's SI. So signal integrity is changing all the time.
All the time.
So, so really, I guess the other advice I would give, and strong advice to give, is get yourself on a materials course. Go to talk to one of the manufacturers, talk to one of the PCB shops, and get yourself on one of the courses so you can actually get an update on where things are now, and ask your questions, because I'm more than happy to help in this regard as well, as will be most manufacturers of materials. We're delighted to impart what knowledge we can to try and help the design community, because we know it's a difficult area to work in now. So whatever you need to know, please talk to the manufacturers and ask their advice.
And I will tell you, as an ex-manufacturer for many years, that I did indeed learn a lot from the people that were producing it on the shop floor, but also what I know about the compositions, a little bit that I can track with you, Alan, came from knowing people like you. It was coming from the substrate manufacturer that could teach me about how this material is produced, how it impacted signal integrity, and some of these things. So I would echo your good advice to, if you have the chance to talk to, I have this mantra, being an ex-board person, go to your board shop. to always, partner closely and take time to have those conversations, but also to talk to people like you is a great education to know how these things are produced. Like the low profile things you were talking about, that really helped me.
Yeah, it's a very narrow field, but it's a very deep field actually, and there's a lot of knowledge in there. I spent my entire career doing this, so that's all I know really. But at least it's something I do know something about.
Well, before we close, the other thing I wanted to touch about, the other role you play in your life is the chairman of the EIPC. Can you tell us a little bit about EIPC? And I know you have an upcoming summer conference, and just touch on that a little bit.
Yes, the EIPC is the European Institute for the PCB community. Our role is to promote electronics, PCB-based electronics in Europe. We've been around for 51 years now, so we celebrated our anniversary last year. And we have a group of primarily PCB producers, their suppliers, and the users and the assemblers. So we cover the entire supply chain, but we are primarily focused on the PCB. So anybody who's involved with PCBs, either designing, specifying, using, in the PCB area, is welcome to come to our events. We hold 2 conferences every year. We just had one in Milan in February, and our next one will be in Austria, in Leoben, in June the 14th and 15th, where we've been kindly invited by AT&S, which is the biggest grossing PCB shop in Europe, to have a facility tour. So we're really looking forward to going and seeing what they have to say. But we put together technical agendas. We pride ourselves on having a very broad and interesting technical agenda. So they will be doing that. It'll be over 2 days. We also run workshops, we run seminars, and we try wherever we can promote electronics in general and in Europe in particular. So I've been chairman now for, I think it's 7 years, now. I've done, 3 terms, job I really enjoy. It gives me the chance to interact with many parts of the supply chain. We also have strong links, by the way, to the international trade associations. So I was over at the EIPC Apex show in January. Was it January? Yes, January. I'm going off to CPCA, the Chinese show, next week. I'll be at the Japanese show in June, and Taiwan in October, and then December, the Hong Kong show. So we all link together, all the trade associations around the world. There are also the Koreans involved. There's an Indian association as well. I think I've forgotten anybody. I've got them all there. So we work together, and every 3 years we put together a world convention on PCBs. So that's something that we look forward to. The next one will be in Hong Kong, and we're working together with the Hong Kong Association to deliver that. So we believe also strongly in partnerships, I have to say, and these partnerships with our colleagues around the world are very crucial. I think everyone's aware that the volume manufacturing of PCB now is in Asia, more than half now is in China alone. So it's very important to connect with people in these industries and actually understand what they're doing and how we can play our part, because there are technologies which Europe and North America have still running very strongly and exclusively in some areas that we have to maintain, and we must support the supply chain as well. So over years you see the supply chain moving, but there are industries still that we need to strongly support. In Europe, I talk about medical. It would be quite a big area, aerospace, as it will be in the US, military and defense, areas you really don't want to lose the supply chain. You need to hold on to this as well. Yep. So I think it's critical that we do understand the supply chain and find partnerships to basically leverage our businesses and make sure we can continue doing what we do. And we still have, a significant PCB industry in Europe, as in North America. And I think it's incumbent on us to make sure we continue with this, because at least OEMs need to know they can talk to people locally that can help them with their designs, even if it's only the prototyping stage or the small scale production, with the knowledge they may have to move elsewhere later. But this knowledge and this technical capability, I think, is crucial for our industries in Europe and North America. So we strongly support that approach.
And I just have to put in a plug here that if you are in reach of some of these events as designers, even though what Alan's talking about sounds very manufacturing centric, this is where you're going to learn. This is where you're going to learn a lot in 2 or 3 days that will absolutely change the way you design boards. It will make you think differently. If you don't have time to go see your board partners or whatever, you can go to a conference like this, and it's a little like drinking from the fire hose, but you will come away a different designer. So I would encourage designers to jump in. I know it's changed my career to be part of Apex or a lot of these industry associations. I've just been like a sponge, and that's how I learned so much, is rubbing up against these different stakeholders, in the process. So I couldn't encourage designers enough to, and I will share that in the show notes too. Get them signed up on your newsletter and different things so they can plug into your own.
We have a free newsletter every 2 weeks that gives you the latest developments. And, these conferences, you will find the major players, the major board suppliers there, the major material suppliers there as well. So any issues or questions you have, this is the place you will find the answers. We do have design-related papers quite often as well. We have regular papers from the FED, which is the German design authority. Very good quality papers from them. That's their business. We also run technical workshops as well. We're actually just producing one at the moment for designers. So we do technical snapshots and we do design days. So that we're working on delivering a package for designers. Just probably a half a day to 1 day seminar, just to give that step up the ladder and give new designers some basic knowledge, and also designers who've been around for a while some updates on new developments, because things are changing all the time. What we learned 10 years ago probably has moved on a bit. So we're very much involved in education as well. So please connect with us. We'd be delighted to help in any way that we can. And we're international as well. I mentioned Europe, but we have many attendees from North America and from Asia. We had at the last conference, I think there were 18 nations represented.
Wow.
At the last conference.
That's
and
impressive.
Quite for us.
Well, I
know.
know.
Quite a few in Europe, but
I am going to do my darndest. I want to come to your tour, your summer conference, and come to ATS. Yeah. So hopefully we'll maybe, and if we do, maybe we'll do another podcast and talk about that and have some more insights to share with designers. So, well, we are out of time, my friend. This has been rich and wonderful conversation. Alun, thank you so much for sharing all your knowledge and wisdom that you've collected really over so many years. It's been really, really wonderful. Thank you for your generosity.
Oh, it's my pleasure, Judy. Great to talk to you. Thanks a lot.
Well, that's it for the OnTrack podcast today. Thanks so much for joining us. I will be sure to share lots of resources in the show notes. Please join us next time. Remember to subscribe, like, and please comment on subjects you would like to learn about so we can continue to deliver great content for you. Thanks again for joining. Until next time, remember to always stay on track.